Hi, and welcome to the Conditional Probability lecture as part of the Statistical Inference class in the Coursera Data Science specialization. So conditioning is wonderfully illustrated by this XKCD comic here. In this case, two people are standing out in a field right near a tree in the middle of a lightning storm, and one of them says we should go inside. The other one says, well, the chance of getting hit by lightning is only about 1 in 7 million, so we're fine. And the tagline is that the death rate among people who know the statistic is 1 in 6. And what the comic is highlighting is that this person hasn't conditioned on what they know, right? In this case, if you were to condition on the death rate for lightning strikes among people who were standing in fields in lightning storms near trees, would be much higher than 1 in 7 million. Let's go through another example. So a simple conceptual example. So the probability of getting a 1 when rolling a standard die is assumed to be 1/6. Suppose you were given the extra information that the die roll was an odd number, hence a 1, 3, or 5. So someone rolled a die in a way that you couldn't see, and they told you that a 1, 3, or a 5 occurred. Conditional on this new information, you would not say the probability of a 1 is 1/6 anymore. You would now say it's 1/3, equally likely between the 1, the 3, or the 5. And that's what conditional probabilities are giving you. And of course, they have a definition. So let's let B be an event such that the probability of B is greater than 0. And this is important because there's no sense in conditioning on an event that can't happen. Then the conditional probability of an event A, given that B has occurred, is written like this. The probability of A, little horizontal line B, so this is read probability of A, given the event that B has occurred, is equal to the probability of the intersection divided by the probability of B. And we haven't talked about independence yet, but in the event that A and B are unrelated or so-called statistically independent, which we'll define later, then the probability of A given B works out to just be the probability of A. So the new information that B has occurred has given you no information about the probability law governing the event A. So let's just check that conditional probability gives us the answer that we know to be true in the die rolling case. So in our case, B was the event 1, 3, 5. A was the event 1. We want the probability of the event A conditional on the event 1, 3, or 5 having occurred. So in other words, we can say probability of getting a 1 given that we know that the roll is an odd number. That's the probability of A given B, which is the probability of A intersect B over the probability of B. In this case, A happens to lie entirely within B, so the probability of A intersect B is just the probability of A. So that works out to be 1/6, and then the probability of B in the denominator works out to be 3/6, right? 1/6 for each of the 3 mutually exclusive possibilities, which works out to be 1/3, which is what we knew had to be the answer.